Hello everyone. Today we are going to talk about risk measures. A risk measure is a real-valued function of a random variable denoted by the function ρx. For example, moments, expected value of x, variance of x, standard deviation, percentiles are all risk measures. The specific risk measure that we are going to talk about is value at risk. Value at risk at the level p for a random variable x is a risk measure, which is the pth percentile for x. In other words, the value at risk of a random variable is just a fancy name for its percentile. So, in order to find this VARX, or value at risk, we just equate CDF to be p, then we can find the x. Or in other words, value at risk of x is just fx inverse. Another two notes we want to make is that first, value at risk is not the same as variance. Variance is just what we learned before. It's a kind of moment, and value at risk is a percentile. And the graph shows on the slides. It's more a graphic description of how you arrive at the VARX. If you equate the CDF to be p, then you will find x, the position for x. This fx here is just an example. The real fx can be a lot different than this fx. Now let's look at the value at risk for some specific distributions. First one we are going to talk about is exponential distribution. VARX is this. How are we going to prove this? From previous slide, we know the process is first we equate the CDF or fx to be p, then we derive the value of x. For exponential, we know fx is equal so this is p. This part you can find in the table. So e would be equal 1 minus p. Therefore, x is equal theta times log 1 minus p. The process is first equate the CDF to be p, then solve for x. Now look at the value at risk for Pareto distribution. Similarly, we have fx equal p, and fx we know from the table is 1 x plus theta alpha. So theta x plus theta alpha would be 1 minus p. Theta x plus theta will be equal 1 minus p to the power 1 over alpha. So x plus theta will be 1 minus p negative x will be theta minus theta. Now let's look at the value at risk for normal distribution. First, we do the same thing, fx equal p. Now, in this case, fx can be standardized, then it will become phi x minus u omega equal p, then x minus u divided by omega over equal fy negative 1 p, which is zp. From there we can get x is equal u plus cp times omega. Okay, for log normal distribution, it means log x is the normal distribution. Let have u and omega square. Then in this case, we still want to find this equal p, and this we can further express it as this equal p. So then this will be equal inverse of this, which is just this. Then u plus jp times omega. Then x is equal u plus jp omega. So every time we start with fx or fy equal p, this is always our starting point. Then we just deduce the rest. Now let's look at some examples. Losses follow a Pareto distribution with mean 10 and the variance 300. Calculate the value at risk at the level 95% and 99%. So first, according to what's given, we have Ex equal theta. This can be found in the formula sheet. This is equal 10. And also we have variance equal 300, which means Ex squared, which is actually not variance, but let's write it out first. This is the given formula. Variance will be 300 plus Ex squared, which is 100. This is the formula we learned before between the var x is equal Ex squared, actually minus Ex squared. Therefore, Ex squared is 300 plus 100. From these two, we can get say alpha equals 3 and theta equals 20. Once we got this, then variable and risk is easy to calculate. Value at the risk, which has the formula too, is this. This is nothing but putting the formula, putting the value into the formula. So this would calculate as 34.29. Similarly, we'll calculate for 99% VAR X, you will get 72.83. Example B. Losses have a log normal distribution with mean 10 and variance 300. Calculate the value at risk at the security level 95% and 99%. This is actually very similar to previous question. So it gives you Ex. For log normal distribution, Ex is E mu plus square 2. And this is 10. And Ex, this is, again, both will be found in your formula sheet. This will be similarly 300 plus 100 equal 400. Now, in order to solve this, you can use first equation is 1. If second equation 2, then you can use second equation divided by first equation square which means it's 400 divided by 100, which will be equal E. From there, you can calculate omega squared to be 1.774, and you can calculate U to be 1.609. Once you have U and omega, similarly, you just need to look for the formula to calculate this VAR, which is mu plus Z 0.95 omega. Then this you can get to be 34.68. Similarly, if it's 99%, it's 77.36. Now let's learn another concept, tail value at risk, TVAR, or we also call it the conditional tail expectation, CTE. So tail value at the risk of a continuous random variable x at the level p is the conditional expectation TVAR x equal expectation x given that x is greater than VAR p x. It's also called conditional tail expectation CTE. Its average all values above the level p. The second part of this slide is the same as the first part, just another way to describe it. And since it's the expectation of x, given that x greater than VAR p x, therefore, according to conditional probability, the denominator will be the probability of x greater than VAR p x, and the denominator will be the integral of x over the integral of VARP to infinity. It's probably easier if I draw a sheet. So if this is fx and this is the and supposedly this is x, let it give you the probability p and 1 minus p on this side, then VAR and TVAR tail value at risk basically is you integral all this part and you give it an average or expectation, which is probably something like here. So it will be just expectation of this part given this x is greater than VARX, which is this part. So it's basically the average of all this part. Here are some more formulas for this tail value at risk. Mostly it's just repeated what we already said. The tail value at risk is the expectation of x given that x is greater than VARPX. And it can be further deduced by two parts. First, denominator is 1 minus this, which is just the conditional the probability for this x greater than VARP, and for denominator is just integral of x using the fx probability density function. And further, we can deduce it to be this. This is actually the most important part because this is the mean excess loss. If we recall this from note 5, and this can be calculated using the fx function Both lists will be easy to calculate based on the formulas given in the formula sheets. Or you can further look at it this way. So this would be easier to use when it comes to solve a problem, and that's what we are going to do. Before we get to the actual questions, these are a few more formulas for tail value at risk for different distributions. Most can be derived from what we have earlier in previous slides. You should try it if you are not certain. First example, x follows a uniform distribution on 0 to 100. Calculate TVAR 0.95x. So we can draw a picture here. 100 and suppose this is 95 here. So it's asking about TVAR. R95. So according to the definition, it's x given x greater than v 0.95x. And there are a few ways to calculate this. Because this is a uniform distribution, it really is asking what's the average of this x given that x greater than 95. Since it is a uniform distribution, supposedly we could easily look at it, say 97.5, because 95 is the lowest, 100 is the highest, and because of uniform distribution, you can just average them together, so with 97.5. Or if you want to use the formula, it will be equal denominator is the probability of x greater than 95. Nominator will be the integral from 95 to 100 given that x and the density fx dx. And for this, we can either use formula, or you can just use the fx as 100. In this case, fx is just 100 because that's uniform distribution. And this, you can use the uniform distributions formula, or you can easily decide this probability of x greater than 95 would just be 5% because fx is 100. So, and you can calculate this part to be this 9500 x and 100 dx. This will be very easy to calculate. Anyway, you will get the same result, 97.5. Now let's look at example B. Losses follow an exponential distribution with mean 1000. Calculate the TVARPX at level 95% and 99%. So first of all, this question can be easily answered as long as you have the formula sheet, which give you this TAR. It gives you the formula TARPX. So all you need to do is just put in the numbers in. First from here we can decide theta is equal 1000 because for exponential distribution mean is the theta. Now from here you can put 1000 is theta log 1 minus p is 95% plus 1000. You can get 3996, And similarly for TVAR 99%, you just apply the same formula except you use 99 instead of 95, then you will get the 5605. And just for clarification, there are two formula sheets. One is formula sheet for ASTM. One is formula sheet for FAMS shorten. This is the sheet that has this formula, the first one. Both will be on my website. I will upload both in under the SOA document. Now let's look at example C. Losses follow a Pareto distribution with a mean 10 and variance 300. Calculate the TVARPX at the level 95% and 99%. Again, this can be utilized in the formula to calculate easily. This formula is in the formula sheet for a shortened exam. But first, to solve this problem, we need to find out alpha and theta for a Pareto distribution. But this exercise we already done previously. We find out Ex is theta equal alpha minus 1 equal 10, and Ex squared is 2 theta squared alpha minus 1 alpha minus 2, and it's equal 300 plus 100 equal 400. From these two, we can calculate alpha is 3, theta is 20. Then the rest is easy. Really, just need to apply this formula here. VAR X plus so I will leave this part to you. It's just replacing all the letters with actual alpha and theta, then you will get 61.443 for 95%. For 99%, you will get the value to be 119.25. Now let's look at example D. Losses follow a normal distribution with a mean 10 and variance 300. Calculate the TVARP, their value at risk for level 95 and 99%. Again, we can get mu is 10 according to the information, and omega will be square root of 300 since variance is 300. And for this, tail value at risk would equal omega 1 minus p phi zp, where phi zp is this is a normal distribution formula. So from here, for 95%, you can have 10, mu is 10 plus 300, 1 minus 95, and 5. This you have to find from the table. Again, the final will be 45.73 for 95%. If it's 99%, you will get 50 for 99%. Example E. Losses follow a log normal distribution with mean 10 and variance 300. calculate the tail value at the risk at the 95% and 99%. So this is similar, very similar. EX, we first find EX based on log normal distribution, and EX squared from here we can get mu is equal 1.6, omega is equal 1.1774. Now tail value at risk is this according to the formula. Then the rest I will let you guys finish it, but for 95% is not answer is 63.84. For 99% answer is 125.10. The last concept in this lesson is tail distribution. The tail of a distribution is the portion of the distribution corresponding to large values of a random variable. The bigger the tail weight of the distribution, the more provision of high claims. Random variables tend to assign higher probability to larger values are said to be heavy-tailed. In the insurance industry, for example, in the P&C world, where larger claim is very much the concern of the actuary because it impacts how much you will pay. For example, in Florida, hurricane season comes, then there are lots of claims, and the tail claim means they are paying more. Eventually, this driven the profit of an insurance company. That's why it's very much focus of the actuaries. They want to understand how many percentage of these larger claims will be, or how much will be the heavy claims, and whether it will drive the company's profit, and whether you should reserve more for tail distributions. These kind of things. Heavy tail behavior is typically associated with large value of quantities such as the coefficient of variance, the skewness, and the kurtosis. Coefficient of variation CV equal omega over mu measure the extent of variability relative to the mean. Skewness is a measure of symmetry, or more precisely the lack of symmetry. Kurtosis is a measure of whether the data are heavy tail or light tail relative to a normal distribution. You probably remember this concept in previous lessons. But here, kurtosis is a measure of whether the data are heavy tail or high tail relative to a normal distribution. So when it comes, you have to calculate the kurtosis in order to understand whether the data are heavy-tailed or not. Data sets with high kurtosis tend to have heavy tails or outliers, and that's what we should pay attention to.